Every software engineer starts with a comfortable illusion. You write your application, run it on your local machine, and it executes your logic flawlessly. The code is clean, the tests pass, and the environment is entirely under your control. Then, that exact same code is deployed to production, exposed to the wild. Instantly, it is hit with thousands of concurrent user requests. In this environment, the elegance of your application code offers zero protection against reality. The most pristine functions cannot stop a network partition, unlock a deadlocked database, or keep a failing drive spinning. Surviving these physical constraints requires a different discipline entirely: system design. This is the process of deciding how the parts of a system communicate, where data lives, and how traffic flows before a single line of code is written. Large-scale software architecture abandons the pursuit of perfect logic. Instead, it focuses on managing unavoidable physical limitations and mitigating partial failures. When you build distributed systems, you are bound by a strict rule. It is mathematically and operationally impossible to maximize every performance metric at the same time. This chart shows the 5 core dimensions we use to evaluate architecture. We have scalability to handle growth, reliability for correct behavior, availability to remain responsive, fault tolerance to survive hardware crashes, and maintainability so engineers can update the system. These properties exist in continuous tension. If you demand strict data consistency, ensuring every single user sees exactly the same information at the exact same moment, you force the system to wait for data to synchronize. That waiting increases latency and directly degrades availability. Every database, cache, or load balancer you add to an architecture is an explicit intervention. You are manipulating these tension lines to solve a specific problem. You cannot engineer a flawless design. You must evaluate the business requirements, understand the constraints, and deliberately choose the right compromise. To see how these trade-offs dictate architecture, let's trace the evolution of a food delivery application. Initially, the user base is small. A single application server and a single primary database can easily handle the volume. Then the Friday dinner rush hits. Traffic spikes exponentially. The physical processor on our single server hits maximum utilization, and incoming requests start dropping. Relying on a single machine imposes a hard ceiling on capacity. This is a direct failure of scalability, the system's inability to handle more users without unacceptable degradation. To break through this ceiling, we apply horizontal scaling, adding more servers to share the workload, rather than trying to build one impossibly powerful machine. We insert a load balancer at the front of the architecture. This component intercepts all incoming traffic and evenly distributes it across multiple identical application servers. True scalability means the architecture can dynamically expand capacity to meet demand, keeping the end-user experience completely insulated from the raw volume of traffic. With the application server scaled, the bottleneck moves down the stack. Our primary database is now overwhelmed by thousands of simultaneous requests to read the restaurant menus. Retrieving data directly from a persistent disk is a physically slow operation. Forcing the database to repeatedly read and serve the exact same static menu data to every single user creates massive latency. We solve this by inserting a cache between the servers and the database. The cache stores the menu data in high-speed temporary memory. Now, repeated requests are intercepted and served almost instantly, bypassing the database disk entirely. Next, we attach a read replica to the primary database. We route the remaining read-heavy operations to this duplicate, ensuring that complex database queries don't block critical write operations, like actually placing new orders. These two additions drastically reduce latency, but they force a major structural compromise between performance and data correctness. If a restaurant updates a price on their menu, that change is written to the primary database, but it takes time for that new price to synchronize across the replicas and the cache. During that window, users will see stale data. This is eventual consistency. To keep the application responsive during peak hours, we have deliberately sacrificed strict, instantaneous data accuracy in favor of high throughput and low latency. The system is scaling, but it remains vulnerable. To finalize orders, our application must communicate over the network with an external payment service. Crossing a network to access an external dependency is inherently slower and far less reliable than executing internal code. If that payment service lags or drops the connection, the application server is forced to wait synchronously. It holds its resources open, backing up the queue, which triggers a cascading timeout storm that takes down our entire infrastructure. The architectural fix for this brittleness is asynchronous decoupling. We sever the direct synchronous connection. Now, when a user places an order, the application server simply drops the order details into an asynchronous message queue and immediately responds to the user. Behind the scenes, background workers pick up the order from the queue and handle the slow payment processing completely off-thread. We trade an immediate confirmation for a message queue. By doing so, we guarantee high availability and fault tolerance, allowing the application to keep accepting orders even if the third-party payment gateway completely fails. If we zoom out, we can see the complete architecture we've built. Strip away the specifics of food delivery, and what remains are the universal, canonical layers of a modern production system. This web of load balancers, caches, databases, and queues is not arbitrary. Every layer is scar tissue, a calculated response to a specific constraint of distributed systems. But this resilience comes with a heavy operational tax. We have introduced redundancy, which requires significantly more infrastructure cost, maintenance effort, and synchronization overhead. Professional architects do not view partial failure as a rare anomaly to be avoided. They view it as the default physical state of the network, and they design around it. The most common mistake engineers make is building for the happy path, designing systems that only function if networks are perfect and hardware never crashes. The opposite extreme is just as dangerous. Premature optimization, adding intricate queues and complex replication before the data volume actually demands it, creates enormous technical debt for no real benefit. When production incidents occur, they often look like application bugs, but a timeout storm or an overloaded database usually points back to an unresolved architectural trade-off, coming due under pressure. Mastering system design means abandoning perfectionism. It requires using first principles to identify bottlenecks, accepting hard constraints, and building software that scales deliberately and degrades predictably.